Welcome back, nerds. Today we're gonna take another serious bite out of Unit 1.11. We probably could finish the whole unit, but there's no rush. So we'll get to a certain point and then we'll call it there. And I guess for the rest of the period we'll just hang out or work on the homework or something. Okay. Boink. What we were discussing last time was in behavior asymptotes, specifically slant asymptotes, and how we know when they're occurring. And what we said was we know that a hole happens if you have a zero of the numerator and denominator that cancels away. A vertical asymptote happens if you have a zero of the denominator that doesn't cancel away. And we said we know we have a horizontal asymptote if we have a bottom-heavy function. That means the degree of the denominator is bigger than the degree of the numerator. Or if the degree of the top and bottom are equal to each other, you'd have a horizontal asymptote. Slant asymptotes occur, though, if the degree of the numerator is bigger by 1. And when you have a slant asymptote, you cannot have a horizontal asymptote. You can't have both. The directions for this question say to determine the slant asymptote. We automatically know it has a slant asymptote because it's top heavy. Because the degree of the numerator is larger by 1, we're guaranteed to have a slant asymptote. We find equations of slant asymptotes using long division. Actually, that's how we find the equations of all in behavior asymptotes. It's just that we only do it if they're top heavy. The one thing you have to remember about polynomial long division, though, is that you're not allowed to have gaps in either the divisor or the dividend. Neither of those is allowed to have gaps in it. And what is a gap? A gap would be, bless you, between the beginning and the end. Say you're missing an x term. Like, see how this one, if I cover it up, you go, oh, x squared plus 7. It doesn't have any x's in it. You'd have to hold that spot open with a 0x. The one I asked you to do in the homework has gaps in it. So you have to make sure that you hold those open. Gavin, can I see that real quick? I have no idea. I'm just going to look real fast. When you picked this up, were they already circled?
No.
Oh, okay. So yeah, this is one I have you doing in the homework. This is an x to the 5th. It's missing an x to the 4th, x to the 3rd. Here's its x to the 2. Here's its x to the 1. And it's missing a constant at the end. So when you set this up, first of all, it's not in standard form. It's not in right order. But second of all, when you go to do it, you're going to have a 0x to the 4th, a 0x to the 3rd. And it wouldn't hurt to put a 0 at the end. But that one's got gaps in its grill. Gap teeth smile. There you go. Thank you, sir. This one is not missing anything. So you won't see that happen for this one. Our job when we're doing this long division is to ask ourselves, what would I have to multiply the front of this divisor by to get the front of the dividend? What do I have to multiply x by to get an x squared? X, yeah. So I like to stack my like terms. So I'm going to throw that x right there above that negative 6x. Now we take this x and we distribute it to the x plus 5. Get x squared plus 5x. And subtract straight down. Negative 6x minus 5x. I mean, x squared minus x squared is 0, so that works out fine. Negative 6x minus 5x is negative 11x. Drop down the plus 7. And now it's our job to make this x become a negative 11x. What are we multiplying by? Negative 11. You take your negative 11 and you distribute it here. Negative 11x minus 55. We subtract. Minus negative is plus. So we actually have a negative 11 plus 11, 0. 7 plus 55, 62. So it goes at the end as remainder over divisor. But, yes, Max? Because it's minus negatives, that's plus. This is an in-behavior asymptote. And in-behavior asymptotes are always going to be talking about what's going on when x is gigantic. I mean, huge, Caroline. Huge, okay? You guys might not even remember that guy. The huge Caroline Huge. You guys remember that? His voice? What's that? He is dead, though, now. Pretty sure he died. What? No, the one that goes, it's going to be huge, Caroline. Huge. He was a car salesman guy. No? Maybe I'm getting too old. Donald Trump? No. Oh. It's going to be huge, guys. It's going to be the best wall. No, like. No. Oh, I was talking about he's a car salesman. But anyway, okay, we're so off track. Anyway, this is an in-behavior asymptote talking about what's going to happen when x is gigantic. And because the remainder will always be a rational function, and because the remainder will always be bottom heavy, the remainder will always go to 0 towards the infinities. So your slant asymptote is the divisor without the remainder. Always the remainder goes towards 0. So we can say that the slant asymptote is y equals x minus 11. So a slant asymptote is just a straight line with slope. It's not horizontal. Boom, there it is. Yes, sir. Well, it's not that it doesn't matter. It's that the further away from x equals 0 you get, the less and less it matters. So because we're describing what's happening to our graph at the extreme far left and the extreme far right when x is gigantic, this behaves like this. Okay. Yes, sir.
Will there ever be a time where we have to list the remainder of some asymptote, where it's close enough to 0 where you can't just say it's 0?
So you're talking about if an asymptote is y equals 0?
No, I don't know how to word my question.
Say it one more time. What was the question?
Is there any time we have to list the remainder?
Oh, when you have to say what the remainder is. No, not for in-behavior asymptotes. You won't need to worry about the remainder. Now, if the question is just doing some long division, then the remainder is part of the answer. But if you're doing the long division to find the in-behavior asymptote, then the remainder will always fall off because it won't ever affect the results.
Okay.
Yes? No. So this one's a slant asymptote, meaning linear, because the degree of this is 1, right? The reason why this has a degree 1 asymptote is because this numerator is, the degree of the numerator is 1 more than the degree of the denominator. If the degree of the numerator is 2 more than the degree of the denominator, then you have a quadratic asymptote. If the degree of the top is 3 more, you have a cubic asymptote, so on and so forth. So yeah, the asymptote could be any kind of polynomial, honestly. I don't think we'll be doing anything worse than slant asymptotes in the course, but we could. But I don't think we will. It says find the equations of any asymptotes. Well, right off the jump, we can see there's no horizontal asymptote. We know that because it's top heavy. That can't have a horizontal asymptote. Horizontal asymptotes can only occur under 2 circumstances. Circumstance number 1. It's bottom heavy. Bottom heavy rational functions always go to 0. Y equals 0. So if it's bottom heavy, you have a horizontal asymptote at y equals 0. And the only other way it happens is if the degree of the numerator is equal to the degree of the denominator. When that happens, then it's just the ratio of the leading coefficients. Leading coefficient over leading coefficient. Because it's top heavy, I know I have a slant asymptote. I know for a fact. But it says equations for any asymptotes. That includes verticals. We find vertical asymptotes by saying what makes the denominator equal 0 after the simplifications. So we get to do some factoring. On the bottom, the 2 numbers that multiply to 15 and add to 8 are 3 and 5. On the top, there's a GCF of x. Now I just pretend this is an x squared, this is an x, and there's no x here. There are two numbers that multiply to negative 10 that add to 3. Those are 5 and negative 2. In case you're not seeing what just happened, I took the x out of that, so I was looking at this. I factored x squared plus 3x minus 10. Anyway, what I'm noticing is x plus 5 is on the top and bottom of that fraction. Boop! What did we just make? A hole in the graph. Yep. There is now a hole at x equals negative 5. The question didn't ask us for that. But we know it's a truth. There is going to be a hole at x equals negative 5. Oh, there is still a 0 of the denominator in this simplified form. Right there. That's going to be x equals negative 3. Vertical asymptote. I don't want to write vertical asymptote. I'm just going to write VA. Please write the words out on the test and actual AP exam. Vertical asymptote is happening at x equals negative 3. Now we just need to find the equation of our slant asymptote. We do that with long division. We don't have to do long division here, though. We can actually do long division right here on the stuff that is left over. Because they are basically the same function. We don't have to do it here, we can do it here. So if you distribute this, you get x squared minus 2x. And you notice how it doesn't have a constant at the end? But, we don't want our stuff just hanging. I'm going to put a plus 0 at the end, which you'll need to do in that homework question that I showed you a little bit ago, because it also was missing its constant at the end. I need to make this x become an x squared. What do I need to multiply by? X. Bang. Okay. Take that x, distribute it to the x plus 3. What you're going to get is x squared plus 3x. Subtract straight down. The plus 0 really didn't make all that much of a difference, but I just didn't want anything hanging. Now I need my x to become a negative 5x. It should be super obvious. I have to multiply by negative 5. Do I even need to track down the remainder since I'm just talking about the slant asymptote? No. Because the remainder will always go to 0 at this point. I'll find it because it's good math and it's good notes. Negative 5 times x is negative 5x, and negative 5 times 3 is negative 15. Oops, wrong color. Subtract straight down, and what you get is a remainder of 15. But this part will never matter. It'll always be bottom heavy, so it'll always go to 0 as x gets closer to infinity. So your slant asymptote will just be the, what's it called? Quotient without the remainder. There we go. We have our two asymptotes, a vertical and a slant. Ta-da! Are there any questions about these two questions that I could help with? Something I could clear up for you, or what ifs, or how comes, or anything like that? Nah? Okay. Alrighty. Let's take a gander at these four then. It says determine if you have a horizontal asymptote, a slant asymptote, or neither. If it does have a horizontal asymptote, write down the equation. And I'm also going to say why we know what we know. Because, that's the understanding part. This one here. What I recognize is that the degree of the bottom is larger than the degree of the top. So I'm going to say degree of denominator greater than degree of numerator. In layman's terms, bottom heavy. But you can't say bottom heavy on the AP exam. You need to use actual academic vocabulary. So since it's bottom heavy, we have a horizontal asymptote. What is it? Has to be an equation. Y equals 0. There we go. So we do have a horizontal asymptote at y equals 0. Yes, ma'am. So by definition, when you're looking at bottom heavy, this is always the asymptote. But let's talk about why. Instead of just memorizing it, let's talk about why. All right? Remember, what we're talking about is what's happening as x gets really, really, really big. So as x gets remarkably big, the top of this thing starts to behave like 3x. The bottom of this thing starts to behave like x squared. If you read, and there it is. Now, sorry, you're supposed to be able to see the x. There we go. If you simplify this, it reduces to 3 over x, right? Just because the x on top cancels one of the ones from the bottom. So as x gets bigger and bigger and bigger, this thing looks more and more and more like 3 over x. So imagine you're looking at 3 over x. This is the thought process. And now let x get remarkably big. 10 quadrillion, 100 quadrillion. 3 divided by a number that large is going to be essentially equal to what? There you go, 0. That's why bottom heavy will go to 0. It's because the bottom essentially reaches towards infinity so much faster than the top does. It ends up being small stuff over massive stuff, which will always head to 0. And that's why. So it's better to know that instead of trying to memorize it, yeah. And using that logic, look at this one. As x gets remarkably gigantic, the top starts to look like 5x squared. The bottom starts to look like 2x squared. And what does that reduce to? Well, don't do as a fraction for me. 5 over 2. Because the x squareds would cancel out. And you're left with 5 over 2. So because the degree of the numerator and denominator are equal, there is a horizontal asymptote at the ratio of the coefficients. 5 over 2. You see, as you start talking about x as being really, 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 really big, this thing starts to look more and more and more like 5x squared over 2x squared. And the x squareds cancel out, leaving you just this number. And essentially this says y equals this crapola. Y equals 5 over 2 is the horizontal asymptote. Ta-da! Example C. Top heavy by 1. What kind of asymptote is that going to have? Slant asymptote. So the degree of numerator is 1 more than degree of denominator. So slant asymptote, and we don't need to find it. It just said find the equation of horizontals. You'd have to use long division. It's like 2x plus 7 or something like that. Mm. 2x minus 2. I think. It doesn't matter. We don't need to find it. Want me to move it up? It'll be easier if I move it up. Riley's trying to look around me. And then we got this last one. What's the degree of the numerator? 0. It's not a first degree because there's no x's up there. If there was an x, it'd be x to the first, it'd be degree 1. But because there's no x's, it's degree 0. Bottom heavy. So just like this one, horizontal asymptote at y equals 0. Is there? How would there be neither? What a good question. You know, nobody asked me that last period. You get a piece of scrap paper and give you an example of one that's neither. I'm going to write it factored, okay? That's a quadratic over a linear. So it looks like it'll have a slant asymptote, right? But this cancels, which creates a hole in the graph. So this is actually just the line y equals x plus 5, but it has a hole in it. So it doesn't have a slant asymptote, which is what it appears to have because it's a quadratic over a linear. No, it's actually, it is its own horizontal slant asymptote, excuse me. It's the line y equals x plus 5 with a hole in it at x equals -1. So if you went to graph that, it'd be like, you know, this would be a 5, and then at -1, so it looks like this. I don't know, where's -1? -1 comma 4? It looks like this. So this is a straight line with a hole in it. Yep. Yes, sir?
Will there ever be a question like that?
There could be. I think there's one in your homework actually, and you have to write the equation of it. And so you just do what I just did backwards, and you go, well, I know if it's got a hole in it, then it's got a a 0 that cancels out of the numerator and denominator, and it would be top heavy. Otherwise, there would have been some kind of other asymptotes going on. Flip the page. And all this stuff says is, in order to analyze a rational function, you need to find the asymptotes, the zeros, the symmetry if it has any, increasing, decreasing, positive, negative, just all the things that we know how to do. The end behavior, written as limits, all that stuff. Bad news, everyone. X squared plus 3x minus 2 does not factor. But it does have zeros, real zeros. How do we find solutions to a quadratic that doesn't factor? Quadratic formula. We're going to have to do the quadratic formula. The denominator does factor, though, so we might as well write that. It is a GCF. Why would I want to do that? Because I can see that there is a 0 of the denominator that will not cancel. And I know it doesn't cancel because this doesn't factor. That means we have a vertical asymptote at x equals -2. Instantly, we know it's impossible, because there's not another vertical asymptote, we know it's impossible for this thing to be an even function, because what's on one side of the y-axis will not be exactly the same as what's on the other side of the y-axis. Just throwing that out there. All right, zeros. Let's find the zeros of this thing, and then we'll track down its slant asymptote because it is top heavy. Let's find our zeros. Quadratic formula. X equals -b plus or minus root b squared minus 4ac all over 2a. So that's negative 3 plus or minus square root of 3 squared, 9, minus 4 times 1 times negative 2. All over 2 times 1. That's x equals negative 3 plus or minus the square root of 9 plus 8, 17 over 2. Now, since we're trying to actually sketch this thing, we want to know what that number is. So you would just grab your calculator and you would do negative 3 plus the square root of 17 divided by 2, which, by the way, I have right here. There's negative 3 plus square root of 17 divided by 2. So about 0.562. And then you would do negative 3 minus square root of 17 divided by 2 and get negative 3.562. Let's throw those two zeros on here to the best of our ability. X equals about 1/2. X equals about negative 3.5. There. Make the dots fat. It's hard to argue with them. You know what else is a really easy coordinate to find? We just found the x-intercepts. You know what else is really easy? The y-intercept. If you're on the y-axis, what does x equal? 0. So let's find our y-intercept. You can never have more than 1 because then it's not a function. So plug in x equals 0. Come up here and everywhere you see an x is gone. Poop! Looks to me like it's negative 2 over 4. Negative 1/2. All that's left now is the slant asymptote. Look like you had a question face about that. No? Okay. All that's left is the slant asymptote. We're going to do some long division here. Alrighty, we are trying to make a 2x become an x squared. What are we going to multiply by? 1/2 x. Now you distribute that 1/2 x, and what you get is x squared plus 2x. Subtract straight down. 3x minus 2x is 1x. And then once again, you're trying to make a 2x become an x. So again, plus 1/2. Got this 1/2 multiplier going on. I'm not even going to bother finishing finding the long division. We don't care what the remainder is. It doesn't matter. We have a slant asymptote at y equals 1/2 x plus 1/2. So here's our 1/2 y-intercept. Go up 1, right 2. And then connect those two red dots to the best of your ability with something straight. Use the side of your cell phone or student ID or whatever. There. And now we're ready to get our sketch. See how it goes through those 2 points? It has to go through those 2 points, get infinitely close to these 2 red lines. It has to go through this point and get infinitely close to these 2 red lines. There you go. Turdur. So it's clearly not odd either because it's not centered around the origin. It is an always increasing function. We can see when it's above the x-axis, below the x-axis because we found the zeros. So from negative infinity to negative 3.5-ish, it's negative. And then again from negative 2 to 1/2-ish, it's negative. From negative 3.5 to negative 2, it's positive. And from 1/2-ish to infinity, it's positive. So there it is. But like I said, it's an always increasing. No extrema. You know, just putting it all out there, everything we know about it. What do you think about rational functions? Got them all? Got a lot of stuff going on with them, but hopefully they're there. Can I answer any questions about the last example for rational functions? None at all? All right then. What we're going to do now is we're going to switch gears and start 1.11b. We're not going to finish it, so don't worry. And we're not even going to do much more. We're just going to talk a little bit. I'm going to show you how to use your calculator to do something, and then we're going to call it there. (11b) is essentially about binomial expansion. What is binomial expansion? Binomial expansion is taking any binomial, which is made up of two terms like this, and then raising it to some power, like this. Now, could you FOIL this nastiness out 5 times? You sure could. But wow, would it just be awful. It would be terrible. Just no bueno. And let's see. I'm trying to remember what it would be. You don't need this. I'm just going to show you what it would be if you fully expand it. It would be x to the 5th plus 5x to the 4th times 3. So was that 15x to the 4th plus 10x to the 3rd times 9. So 90x to the 3rd plus 10x squared times 27. 270x squared plus 5x times 81, that's 405, plus 3 to the 5th power. Something went wrong here. No, I did that right. That's the expansion. See, I got that without doing any foiling. But could you imagine how big those numbers got? You know, the number-like terms you'd have to track down? The point is, of course there's a better way of expand binomials rather than brute forcing and going through all the foiling. The way we do it is using Pascal's triangle. Or, even better, just simply using the binomial theorem. Today we're going to just discuss the binomial coefficient. And we're going to do it using this. Do not say this is n over r. That sounds like a fraction. You can say n above r, or you can say what I'm always going to say, n choose r. Because that's what this means, n choose r. N choose r, also known as the choose function, calculates the numbers of ways that small groups can be made out of big groups. For example, in the middle of my room, there are 4 gentlemen sitting there. I could say something like, of these 4 people, I'm going to pick 2 of them. How many different ways could that happen? Well, let's do it. There's 2 different ways to go horizontally, right? So 1, 2. 2 ways to go vertically, 3, 4. And 2 ways to go diagonally, 5, 6. So out of a group of 4, I could choose 2 people 6 different ways. And that's if order doesn't matter. Okay? This is how you calculate that by hand. N must be a whole number. R must be a whole number. They must both be positive, or R could be 0, but they must both be positive unless R is 0, and N must be larger than R. I couldn't say out of a group of 3, how many different ways could I pick 4 people? Well, that's not possible. But I could say out of a group of 4, how many ways could I pick 3 people? You know? This is another way of writing it. NCR. In fact, this is how your calculator writes it. These exclamation points are not excited letters. They mean multiply all the numbers, that number and smaller. It's called a factorial. So what is 5 factorial? Like say n was 5. 5 factorial is 5 times 4 times 3 times 2 times 1. 9 factorial is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1.
All as one number?
You would grab a calculator and see what it equals, essentially.
Which like 9 times 8 and then you do whatever that
Times 7 times 6 times 5 times 4 times 3 times 2 times 1. Yep. Okay. They're big. They're big.
Yeah, that's
okay. Yes, sir.
Does the calculator allow you to put? I remember when I had this refreshers class last year, to calculate factorials, we just put like whatever number we wanted to see what the factorial was and an exclamation point.
Yep, it has the factorials, but you don't even need to do that because it has this function in it. And since we don't need to know how to do this by hand for the AP Calculus exam, AP Pre-Calc exam, I'm not going to make you do it by hand either. Could we do 6 choose 2 by hand? Yes, we can. It's really not bad either. But we don't need to because we don't need to know this formula for the AP Pre-Calc exam. So instead, we'll just use our calculators for it. The choose function is found in the math commands. So you press the math button on the left side, press math, and it's actually a probability thing. So go over to probability, and it's the third one down in CR. Okay, one more time. Math, scroll over to probability, and number 3 in CR. It's also, if you want to use a shortcut menu, alpha window, it's in there as well. See? Alpha, the green button, window, brings up this menu. So alpha window 8 is in CR. Put a 6 here, put a 2 here. This is 6 choose 2. This means how many different ways can you pull a group of 2 from a group of 6 if order doesn't matter? 15 ways. This is known as a binomial coefficient. These numbers are binomial coefficients for the expansion of 5. This one would be the second number in the expansion of 6, is what that essentially is saying. Anyway, 6 choose 2 we got was 15. And this calculator is awesome sauce that you can just go up and highlight and then just edit it. So 9 choose 4. Hit enter again. Bang. On 126. Yeah. Without a calculator, what do you think 3 choose 3 is? 1. Because it literally says, how many different groups of 3 could I pick from 3 people? 1. Also, just so you know, by definition, just so you know, it doesn't matter what n equals. Choose 0 always equals 1.
What if it's 0? Choose n.
The top number has to be bigger. That was one of the rules.
What if it's 0, choose -1?
One of the rules is that the numbers must be positive. I said that too. All right. One other thing you have to know about factorials, just so you know, by definition, 0 factorial equals 1. That's just something that we do in mathematics. So anything choose 0 is always equal to 1, and anything choose itself is always equal to 1. By definition, 0 factorial equals 1. And that is where we're going to call it today. Thank you. Okay, 0 factorial equals 1 because we need it to. So it's by definition.
So you're just making up your own?
No, we're saying by definition, 0 factorial equals 1.
Well, not you, but like mathematicians are just making up their own.
No, we're not making it up. It must. It's one of the rules of the symbol. Okay? That's because there's a much more difficult explanation of what factorial equals, how they're calculated, without saying 5 times 4 times 3 times 2 times 1. That's actually the low-level math way. But there's a much more complex definition for factorial that uses calculus remarkably difficult calculus. And if you do it in that, you see that it equals 1.
Okay.
Anyway, thank you.